Today we're going to learn about confidence intervals for the sigma known case, right? After today, you will be able to do confidence intervals for the sigma known case. However, when you open up Cengage now, like I'm doing right now, the problems in here for confidence intervals all involve the sigma unknown case. So we have to do one little thing to be able to do that. So we'll go ahead and open it up to show you. Hopefully you didn't have any questions on 1 through 4. Everybody hopefully got that. I didn't get any emails from anybody, I don't think. But on number 5, this is a series of confidence intervals, one for 90, one for 95, and one for 99% confidence. And it's for a population mean. And I should probably put it like this. This is my recording screen. But in this one, it's a mean confidence interval because I have a random sample of 25 oak trees, so that's n equal 25. That gives a mean of 64 and a standard deviation of 4. Why is this a sigma unknown case? Why is this a sigma unknown case? Does anybody know? What is sigma? Melissa. What is sigma?
The variance.
Well, not the variance, because that would be sigma squared.
Standard
Oh, there you are. Sorry. The standard deviation of the population or sample. Which one? Population or sample?
The sample.
Well, let's just think about this. Only the Greek gods know things like sigma and mu, right? Greek letters. Greek mu is the symbol M, right? Mu, M, mean. Sigma is the Greek letter S, population standard deviation. Mu, population mean, right? And only the Greek gods know those things, right? And you're not a Greek god, I'm not a Greek god, none of you guys are Greek gods, right? So in reality, we don't know mu and sigma. Only the Greek gods do. And those things are population parameters. So anything in a Greek letter, mu, sigma, beta, which we'll learn about in chapter 15, those are Greek parameters, Greek letters, only known to Greek gods. And our job as a statistician is to sample a population and then estimate mu with X bar. X bar being the sample mean. We're going to estimate sigma with the sample standard deviation S. We're going to estimate beta, a slope parameter in a regression model, with B, its estimate from a sample of data. So we can only dream of knowing sigma, mu, and beta, right? But we can estimate them with X bar, S, and B. Okay? So in this problem, is this a sigma known problem or a sigma known problem? Let's see, William. Oh no, sorry, wrong class. Ethan.
Could you ask me one more time?
Is this a sigma known problem or a sigma unknown problem?
Well, it says standard deviation of 2, so isn't sigma known?
Okay, let's reread the problem real quick. A random sample.
Unknown then?
Yeah, because that sentence starts with a random sample, right?
Right.
In that random sample, we have 25 oak trees. The random sample has a mean of 64. The random sample has a standard deviation of 4. So that would be a sigma unknown problem, right? What about the next one? Is this a mean confidence interval? Or is this a proportions confidence interval? It's a proportions confidence interval, right? Because it actually says it, right? Proportion. Yeah, it says proportion. So this is a kind of our third case of confidence intervals for chapter 8. Okay. Proportion problems always consider they're always considered sigma known problems because you take that sample proportion and you use it to calculate sigma like we did in case 1, right? Like we did on Tuesday. We used the P to compute the sigma squared, and we took the square root of the sigma to get the sigma, right? So proportions problems are always Z problems, right? Because we're going to compute sigma from the sample proportion, all right? What about number 7? What kind of problem is this? A survey of 36 sales supervisors had a mean of 5591 and a standard deviation of 1842. What kind of problem is this? Michael. Michael, here? No. Tyler. What kind of problem is this? Is this a mean confidence interval or is it a proportion confidence interval? Mean confidence interval. Now, is this a sample standard deviation or is this a population standard deviation? Sample. It's a sample standard deviation. So this is not a sigma known problem. Sigma unknown problem. What about 8? What is this one? Again, it's a mean. Confidence interval for a mean, right? And a random sample has 12 items in it, 12 observations in it. A mean of 2.64 hours. A standard deviation of 1.27 hours. Is that a sample standard deviation or is it a population standard deviation? A random sample standard deviation, so sample standard deviation. Sigma unknown. None of these problems here are sigma known. But our first case today, case 2 on my website, we're going to do case 2 here. Case 2 on my website is a sigma known problem. How do we know, Trevor, that this is a sigma known problem?
Gives you sigma?
Yeah, sigma squared is 25. And I gotta fix this, by the way. I took the textbook's restaurant data and made it into a simulation, so you can delete that. Okay. So you should delete that sentence.
What sentence? Yeah.
The middle one.
Data were collected.
Yeah. Yeah.
If we're gonna cut out.
Now notice what happens when I hit F9. Everybody hit F9. If you have a laptop, you might have to do function F9, right? Function F9. What happens to my data in column A?
Nothing happens then.
When you hit function F9?
Moves up.
Moves up? Or the numbers change?
Numbers change.
Does everybody's numbers change? So what's going on here? Every time you hit F9 or function F9, you're generating a new sample of 49 items. How many times can I ask people who live in Atlanta, right, how many people live in Atlanta? Millions? 4 or 5 million people? Maybe, right? How many times can I randomly sample that population regarding the amount of money they spend at restaurants per meal? Can I pick 49 people today and ask those 49 people how much money they spent? Yeah. Tomorrow, can I go to the phone book and pick 49 new names? Yeah, and I can ask them how much money they spent in Atlanta, right? So every time you hit F9, what are you generating?
A new sample.
A new sample of 49, right? And the numbers here are how much people randomly picked from the population in Atlanta who went out and spent money at Atlanta area restaurant. And that amount there is how much they spent on a meal. Okay? So the first thing I want to do is I'm going to have you guys calculate the mean of the sample. We're going to call this a sample mean. Also known as what? Is it known as mu or x bar, Kyle?
The X value.
X bar. X bar corresponds to the sample mean. Mu is what we want to know. There's no way we can know mu, right? Because mu is a Greek letter. A Greek parameter. A Greek letter. Only the Greek gods know it. And how many people in here are Greek gods? Maybe on Facebook you think you're a Greek god, but, right? You're a god in your little world on Facebook or Instagram or Twitter, right? When you tweet stuff, you think the whole world's listening, right? But some people do, right? I still don't know how Twitter works. I don't know what pound sign means. I don't know what at means. I just say something funny on what I think is funny on Twitter, and that goes along with a story I read. Yeah. But on your Twitter account, on your social media accounts, you might think you're a god, but you're really not, right? We're not Greek gods, so we don't know mu, we don't know sigma, and we don't know betas, right? But we can estimate them, right? So what are we doing here? What's the goal of the confidence interval? The mu is in between this confidence interval, right? We're hoping. So what does the confidence interval give us? Maybe it gives us a worst case scenario and a best case scenario. If you're single and in college and want to take a girl on a date, or you want to go on a date with a boy, right? You only have so much money. So worst case scenario would maybe be the upper limit. The best case scenario would be the lower limit, right? So we're trying to get an idea of what mu is, the average meal price in Atlanta. We'll never know that true average, but we can sample people eating at restaurants to get an idea of what that true population mean is. A best case and worst case scenario. Have you guys ever heard those phrases before? You got a worst case scenario and a best case scenario, right? Yeah.
Why don't we just go straight to the actual restaurants in Atlanta?
Well, we could do
Just
that.
take the average of each store.
But this is how much the average consumer in Atlanta spends.
Well, yeah, but can't we find the same data
Well,
out from-
suppose one restaurant has 1,000 customers a day, and another restaurant only has 10 customers a day, right? So we'd have to do what?
add them together?
And maybe the restaurant with 10 customers a day, the average meal price is $150, right? So you're not really, when you do that, you're not really finding the average that restaurant goers spend in Atlanta, right? You're basically, what you're doing is you're answering a different question. How much does each restaurant charge for a meal? Right? That's a different question. What's the average?
The exact same as
No, because customers, you might go to McDonald's all the time. That would pull down the average, right? Whereas I might go to Ruth Chris Steakhouse. That would pull up the average, right? But if you just ask restaurants their average meal price,
okay.
right? You're not accounting for what? Customer choices, right? And there's a lot of upscale restaurants with very low customer rates, right? Customers per hour. Then that would have a really high average, right?
And that's huge in Atlanta.
Yeah. And it would, yeah. Mhm. So we want to know what the average consumer spends on a meal in Atlanta, not what the average restaurant charges for their meal in Atlanta. Okay? So I want every type sample mean, which is X bar, and I want you to type sample standard deviation.
Do we want to hit equals first?
Well, I'm just labeling the chart, the table. I'm just labeling it. Okay, now what do we expect the sample standard deviation to be close to in value? What do we expect to be close to in value? Zhang? Is that right? Zhang? Not here? Taylor?
I'm gonna say 5,
We expect it to be close to 5. Why?
because sigma equals 5.
Yeah, right. Is it going to be, what's the probability it equals 5?
Right.
What's the probability that it equals 5, the sample standard deviation?
Is
question?
Yeah. What is the probability? What is the probability? Let me rephrase it. What is the probability that the sample standard deviation equals 5 precisely?
95%?
Nope, 0.
Okay.
Why do I say 0?
Because it'll never equal to 5 and it will never go lower than 0.
Well, it'll probably be some decimal. And how many numbers?
You're never gonna hit the true mean.
Yeah. Well, let's look about it this way. How many 5s are on the number line? How many 5s are on the number line?
1.
1 5 on the number line, right? How many real numbers are between 0 and 10? Infinite many, right? Sample standard deviation is going to be one of those infinite many numbers. What is 1 divided by infinity? 0. 1 divided by infinity. 1 divided by 10 is what? 0.1. 1 divided by 100 is 0.01. 1 divided by a billion is 0.000000. Yada, 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 0, 1, right? 1 divided by a quadrillion is 0.00, yada, 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 0, 1. What are these numbers getting close to? 0. So 1 divided by infinity is 0, right? Okay? So there's infinite many choices between 0 and 10. 0 and infinity, there's infinite many choices. And there's only 1 5 in the positive number line. So the probability is 0, right? Okay, cool. So let's continue. Okay, now if I type equal average and then go over here and get the average, right? I get 26.51. Equal average A2 to A50, right? That's the X bar. That's the X bar.
What if we,
Now notice what happens when I randomly sample the population in a simulated way by hitting F9. Here's a new random sample of, here's a new random sample, whoops, what's going on here? Here's a new random sample of 49 customers, 49 more customers, 49 other customers, 49 other customers, 49 other customers. What is happening in the mean? What does it appear like it's hovering near? What number does it seem to be hovering near?
24 to 26, 25.
I bet the mean of this thing is probably 26 somewhere in there, right? About 26. Okay. Now, in order to prevent that from, in order for you to not continuously randomly sample this population in a simulated way, what I want you to do is click on column A, right-click, copy, and then right-click on column A again, and I want you to pick Paste Special. Mac, Paste Special, nerdy PCs, you can just do that, 1, 2, 3. But for a Mac, you have to pick Paste Special, and then probably come down here and do values. I'm not sure what you guys are seeing. You want to paste the things back as values. Okay, so now when I hit F9, what happens? Now I'm working with a given, specific sample, right? You guys see it? How many people have a sample mean of 26.65? Anybody? Raise your hand if you have a sample mean of 26.65. Nobody, right? How many people are below this number? How many's mean? Okay, so you guys' means are below my mean, right? How many people have a mean above this? Okay, good. So my mean is probably on the high end, right? There's like 4 people that raise their hand. So my mean is probably on the high end. So maybe the true population mean is, I don't know, 26.3. We don't know, do we? We won't know, right? Now, if you click on the code before you froze the data, then you would probably be able to figure out what the mean is, right? Okay. So now what I want to do is I want to get a bunch of means here. And maybe we'll do all y'all. We'll do 15 means. I'm going to just go through the list here. I'm starting over. Cassie, what's your sample mean? 25.11. Emily, what's your sample mean?
25.73.
25.73. Cody, what's your sample mean?
25.21.
25.21. Shelby, what's your sample mean?
25.63.
25.63. Nick, what's your sample mean?
25.59.
25.59. Got a lot of 25s here, right? Ashley. Ashley here? Oh.
27.04.
20. Oh, you're the wild child.
Joe.
David, what's your sample mean?
25.46.
25.46?
Yeah.
46, okay. Anija. I probably hammered that up. Not here. Derek. Not here. Tyler. Tyler?
I'm right here.
Oh, Tyler.
27.2.
Tyler K. Yeah, okay. Oh, yeah, K. Kaysville, right. What is it?
27.2.
27.2. And then Megan, what's your sample mean? Do I need to do any more? Can I yada yada this? I'm going to yada yada this. Also, there's 26 people in here. So we're going to do a dot, dot, dot. Okay, and then my sample mean is 26.65. Okay, so what are these numbers hovering near?
25.
What's the max?
27.04.
Equal max. We'll assume the ones in between are between the min and the max, right? The min. Now, these are the means, right? These are the sample means, right? And then how about the mean of the means? Mean of the means. How about the mean of the means? Equal average. Do you think the mean of the means provides an even better estimate of the true mean? Right? Individually, these items don't provide a very good estimate of the true mean, do they? Individually. But the means are better estimates of the mean. What do you think the mean of the means is? Even better, right?
Did you include the min and max in that though? That's what it figured it.
What's that?
You included your min and max.
Oh, I did.
Yeah.
Sorry. I just make sure you guys are paying attention. And we don't have all of them, right? We don't have all of them. What about the standard deviation of the means? I'm just going to use the,
Standard S? Or is it
Yeah.
D?
I'm going to just use S. Okay. Standard deviation of the means. Okay. So our max 27.2, our minimum is 25.11. The mean of the means is basically 26. What do you guys think? What do you guys think I chose as the true mean because I was playing the role of a Greek god when I pick what mu is in the simulation? I'm essentially playing the role of a Greek god. Maybe the Greek god of statistics. I'm not sure who that is. What is Zeus? Let me know.
Reason.
Zeus is the Greek god of what?
Reason.
Reason. Maybe. What about Nike? What is Nike? The Greek god of what? Maybe Nike is the Greek god of statistics. So I'm Zeus, or not Zeus, Nike.
Goddess.
Huh?
The goddess.
Oh, it's a goddess. Well,
Of
okay.
victory.
All right, I'm not Nike. Okay, so maybe Bikey is the Greek god of statistics, right? And I'll be Bikey. And maybe I pick 26 as the true mean for the simulation, right? So our mean of means is really close to 26, right? The max and the minimum suggest if it's a symmetric distribution, that 26 is probably a pretty good estimate of the true mean. Okay, you guys understand what's going on? Do you guys see it? So we got a pile up, right? There's a lot of them that are really close to 26, right? But occasionally we have a 27.2. Occasionally we have a 25.11. But the other ones are piling up where? In the middle, aren't they? So when you have one over here, one high one, and a bunch piling up in the middle, and then one out here that's really low, what does that translate into? What am I doing here with my hand? A bell curve. So why is there a hump in the bell curve with regard to sample means? That's where we have the highest frequency, right? The highest frequency is where they're piling up. Literally piling up. The sample means are literally piling up near the mean. Right? And then the tail's off because probably the probability that you have an average of 4 is 0, right? The probability you have an average of 50 is 0, right? Because the true average is 26, which none of us know. Unless you play the Greek god of statistics, Bikey, right? And you pick 26, right? For the simulation. You guys all understand sampling distributions? Okay, is that better than what the book does? Hopefully. Yeah. I've just been doing this for a while. Okay, so we're going to go ahead and delete this stuff. We don't need it anymore. Oh, actually don't delete it. I want the standard deviation of the means to stay there. Now, the sample standard deviation, what do you guys get for your sample standard deviation? STDEV.S, what do you guys get for it? Is it close to 5? Mine's pretty close to 5. So if I go through and make the same table, I'll just point at you guys and you guys yell out your standard deviation of your sample.
4.67.
4.67?
5.57.
5.57? Sample standard deviation? Oh, all you do is you type equal stdev.s, parenthesis, and then highlight the data. And it's an A2 to A50. You got it? 5.38?
5.58.
5.58?
5.58. 5.20.
Well, are you guys actually equal?
Yeah, kind of.
Add a couple more decimal places.
5.57588. 5.5847.
So you're not equal.
5.20.
5.17. 5.76.
What do you guys think the true population mean or standard deviation is?
4.88.
That's kind of low. What's going on over there?
5.39.
4.86. 5.25.
5.72. 5.398. 5.43. 5.17.
So what's going on? All these sample standard deviations are pretty close to the true population standard deviation of 5, right? So again, what do we have? We have a pile up, right? Now, can a standard deviation be negative? How do we calculate it? We take the first observation, 26.99, subtract from that 26.65, then what do we do with that difference? We square it. If that's below the mean, the deviation is negative. If the observation is above the mean, it's positive. Either way, when we square, what happens to the negative? Goes away. So if I subtract the mean from this, if I subtract the mean from that, positive. Negative deviation from the mean, right? But I'm squaring all those deviations. So do I have any negative numbers when I sum them up? No. When I divide by n minus 1, can n be less than 1? No. N starts at 0, which means you don't have a sample, right? That doesn't make any sense. And you don't want a sample of 1, right? Sample of 1 doesn't, I mean, look at it. Is that a good estimate of the true mean? Probably not. Is that a good estimate of the true mean? Probably not. So you don't want samples of 1. So n minus 1 is positive. The sum of the squared deviations of the mean are positive. That ratio is positive. So can the standard deviation be negative? No. So the pileup is what? So the distribution kind of looks like this. It's heavily skewed. Whoops, sorry. It starts at 0. There's a pile up, and then it goes to infinity. Okay, that's the distribution of the standard deviation. Okay. Cool. So now you guys know about sampling distributions of S and sampling distributions of X bar, right? Okay, now what is a confidence interval? What I want you guys to do is open up PowerPoint 8. And we'll look at what confidence intervals are. If you read the book, then this will look familiar. If you didn't read the book, then you might have your eyes crossed at this moment in time. Okay, that's a confidence interval right here.
What number are you on?
Slide 14. X bar plus or minus Z, which is the Z that we were talking about on Tuesday, sigma divided by the square root of n, right? There's your confidence interval. How many numbers are in the confidence interval? Megan? Not here? Okay. Matthew? Kara? Kara?
Car,
Kara?
49.
What was the question again? I forgot.
How many were in the same?
Oh, no. How many numbers in the confidence interval?
Oh,
How many numbers in the confidence interval?
1.
When you do all the addition and subtraction, multiplication, whatever, you do all the arithmetic, how many numbers will you end up with?
1.
Well, let's talk about it. Well, the first time you're going to do X bar plus Z.
Oh, 2.
Yeah, so 2, right? The next time you're going to do X bar minus Z times sigma divided by the square root of n. All right? So there's 2 numbers there, right? There's an upper limit and the lower limit. Schaefer. Schaefer here? No? Emily. Emily, okay. Emily, all right. This is my second time around, I think. Right?
There's 2 Emilys.
Oh, there is? Emily Nelson?
She's gone.
Okay. Chandler, right here? Yeah, Chandler. Chandler, what was this ratio called? What was that ratio called? The sigma divided by square root of n. What was that called?
The population standard deviation.
Okay, this right here is the standard deviation, right?
Yeah.
But when you divide by square root of n, what do you have? You have not the standard deviation, you have the standard, not the standard deviation, you have the standard error, right? Standard error. Okay, everybody got that? When you divide by the square root of n, you have the standard error. What is another name for the standard error? This right here is the standard deviation of x. Another name for this ratio here is the standard deviation of x bar. So this ratio here has 2 names, P. Diddy and Sean Puffy Combs. I'm sorry, Beyonce and Sasha Fierce. No, I'm sorry. Standard error, it's actually standard error, or you could call it the standard deviation of x bar. And what is x bar? A mean. The standard deviation of the sample mean. When I multiply by z, when I multiply the standard error by z, what do I get, Julie?
The
Margin of error. The standard of error becomes the margin of error. Now, if z happens to be 1, then the margin of error and standard error are the same, right? If z's 1, margin of error, standard error are the same. But rarely have I ever used a z value of 1, right? Okay, so I'm going to copy this. Oh, I got to pull up my snippet tool. I'm going to paste or pin that to my. I'm going to copy that into Excel. I'm going to pin that to the taskbar. Okay, that's my confidence interval. Kind of cool, huh? I love this tool, by the way. If you're making PowerPoints and you copy text from Word into PowerPoint, it kind of gets messed up, right? But if you have it formatted in Word, the best way to make a PowerPoint or a table is to copy it with the snipping tool and then paste it into PowerPoint. Then you have to worry about formatting it. You don't have to worry about the formatting changes, right? So it's really cool. Okay, let me ask you a question. The Cengage Now homework, all the Cengage Now homework involves what?
Standard deviations.
Of the sample or the population?
Samples.
So these are all sigma unknown problems, right? All the problems, except for the proportions problems, where you have to calculate sigma from p bar and whatnot. All the mean confidence interval problems in the Cengage Now homework involve sigma unknown. So what do you do if you don't know what sigma is? If you don't know what sigma is, how do you calculate sigma divided by square root of n? Can you calculate it? No. So what do you do? Solve. Well, we're not Greek gods. We're not Greek gods, right? We'll never know sigma. Do you throw your hands in the air and wave them like you just don't care?
Yes.
Do you walk out the room with throwing your pencils? I quit. No, what can you do?
Email you and say, what is this?
No.
Use what you said.
What is S? What is S?
Unknown.
S stands for standard deviation, whether it's Greek or whether it's Times New Roman and italicized. Italicized Times New Roman S means standard deviation. Sigma means what? Everybody, yell it! Standard deviation! What is this?
Standard deviation.
Standard deviation. What is this?
Standard deviation.
Okay, which one is this? Population or sample?
Sample.
Greek letter. Only Greek gods know these parameters. It's a parameter, population, standard deviation. S can be calculated by mere mortals if you have a sample. And we have a sample of size n. In our case, 49, right? So we can calculate this standard deviation from the sample. Now, if you know sigma, what do you use? Here's my wrap to help you out what to do. This is how you figure out which confidence interval to use. If you know sigma, what do you use? Z. Okay? If you don't know sigma, what do you use? T, yo. See, Z and T rhyme. Right? Z and T rhyme. Now, we could have called it G. Does anyone know why we could have called it G? Yes. Not because the guy wore a G string. Right? Statisticians are goofy guys. They may walk around the house with G strings on. I don't know. Right? I don't. But this guy might have. I don't know if he did or not. Right? But it could have been called the G distribution rather than the T distribution because he invented this distribution, or he derived it when he was working at Guinness Beer. Okay. And he published his finding under the pseudonym Student T. But I think it had something to do with Guinness Beer not knowing if the guy is a crackpot or not. Because, have you ever looked at some statisticians or mathematicians? Like my abstract algebra teacher from Idaho State. Gray hair sticking straight up, glasses down to here, walking around like this, 6'4". You know, they're kind of like goofy guys. So you don't know if they're smoking crack or not, right? So if you don't know sigma,
Find out.
you have to calculate it, right? From the sample, in which case it's called a sample standard deviation. I'm going to copy this one too. I'm going to paste it right next to that. So I have the confidence interval for the sigma known case, and I have the confidence interval for the sigma unknown case. What's the difference? Well, because sigma is given to me, it's 5. Which one do I use? That one or this one? This one, right? I use this one. The one on the left. And don't tell me you're not irreplaceable, as Beyonce sings in that video. Now, if I don't know sigma, which one do I use? The sample standard deviation, which is 4.8967, or do I use, whoops, this is funny. I think it's funny. What is the square root of question mark squared? If you're taking the square root of question mark squared, what would it be? Question mark. So if sigma squared is question mark squared, do you plug in question mark or do you plug in 4.8967? Yeah. So if you plug a number into this equation, do you use the t table or do you use the z table? You use the t table. You guys got it? So after we do this case, it might be difficult, but you will be able to do all of the mean confidence intervals for the sigma unknown case. And we're going to do that case on Tuesday, the sigma unknown case. We're going to do that on Tuesday. But I want you to try a couple of them over the weekend, right? See if you can figure it out, right? Fortunately, we know sigma, right? Zeus came down and said, Hal and his students, sigma squared is 25, right? So fortunately, Zeus came down and told us that sigma squared is 25, right? Which means sigma is 5, correct?
Yes.
So that means we use the sigma known case, right? We use z because we know sigma. We don't need to worry about the t, right? We use sigma. So what am I going to do over here? I'm going to type in population, where are the caps? Population standard deviation. And what is it equal to? Everybody, what's it equal to? 5. And then we're going to do, so what's the next thing that we calculate in this thing here? We have sigma, right? This is in Excel. This is stdev.s, right? And this is stdev.p, right? But outside Excel, this is sigma, and that's s. Why the s and sigma? They're both letters for the letter s. One's in Greek and one's in one's in Arial font, right? Arial font S. Greek letter S. Standard deviation, standard deviation. Greek letter, only Greek gods know the parameters, the Greek letters. Population. Not a Greek letter, mere mortals can compute these things, provided they learn something in my class, right? My brother Ryan can't calculate this, but I can, because I've had years and years and years of training, right? Okay, so what's the next component in computing the confidence interval? What's the next component? Who's the next contestant on The Price is Right? Did I ask Melissa a question just now?
Yeah.
Melissa? Where's Melissa at again? Oh, Melissa, okay. I have to ask you a question. You almost got out of it. What is this thing called again? This ratio? This is a standard deviation up here, right?
Yeah.
But when I divide by the square root of n, it's called a standard. Standard. When you type 5 instead of 4, what'd you do? You made a mistake. Another name for mistake is error. This ratio is a standard error, right? What's this ratio called? Standard error. But it's the estimated standard error, right? This is the estimated standard error because this is an estimate of sigma. You guys got that? This is the standard error. This is an estimate of that standard error. This comes from the sample. This comes from Zeus. Sigma is known to be 25. The square root of 25, sorry, 25. The square root of 25. 5. Zeus can't do arithmetic, but he knows the population variance, 25. Okay? So we need to calculate the standard error, right? If we calculate the standard error using sigma, how do we do it, Ethan?
Using sigma?
Yeah.
The sigma over square root of n.
So I'm going to type equal, and I'm going to go up 1 to sigma, right? I'm going to hit divide on my keyboard. Then I'm going to type square root. So what is SQRT as a text message? If you text that to your buddy, what would he think? SQRT? You guys got dirty minds. So if you texted me, I would think, oh, you want to take the square root? I'd ask you, what number do you want to take the square root of? That's what I would be thinking.
Okay, what's your phone number then?
If you text me SQRT, I'm going to think of it as a question. And I'm going to go, okay, you want the square root of what number? And I'll be waiting for a number. I'll be waiting for a number. Where's the number? I want to take the square root of it. Okay, that's how I take that. That's how I take that text.
Yeah.
And what is n here, Ethan? 49. Okay, that right there. Wow, that's pretty cool. What was the other name? What was the other name for the standard error that we talked about? What's the other name for standard error? This right here is a standard error, right? That right there is a standard deviation of x. This whole thing is a standard deviation of what? X bar. Do you guys see that? This is a standard deviation of x. The thing is called, the ratio is called the standard error, aka, not P. Diddy, sorry. This ratio is also known as the standard deviation of x bar. And x bar is a mean. So look at this number relative to that number. Whoops. Ah, dang it. Huh, that's weird. I'll put it in yellow. Why are those two numbers close to each other? What is this over here? This is standard deviation of what? It's standard deviation of our means, right? It's the standard deviation of our means, our sample means, right? Why is this so close to that? Because the standard errors of their name is what? Everybody, you got to say it. If you can say it, you can do it. If you say it, you can do it. That's the Hal Snarr trained to statistics success. If you say it, you can do it. The other name for standard error is the standard deviation of x bar. And x bar is a mean. So this right here is an estimate of that. Kind of cool, isn't it? That's why they're so close together. That kind of comes up in when we talk about ANOVA later on. We'll talk about that. Okay? So there's a reason why those two numbers are close. Another estimate of this number, Melissa mentioned it. Tyler, if I don't know sigma, what do I got to use? If I don't know sigma. If I don't know that, what do I use instead? S. And what do I divide that by?
The square root of n.
Square root of 49 in this case, right? So all three of these numbers are close, aren't they? So this is, if you only have one sample, this is how you can estimate the standard error, right? Here we have one sample, right? Why do I say we have one sample here? We have one sample over here, right? But over here, this is another way to estimate the standard deviation of the means, or the standard error. Why? Here I got 26 means, right? 26 means. I got 26 means, right? So both of these, if I have one mean, if I have one sample, I use this to estimate the standard error. If I have many means, I can, in a sense, use the standard deviation of those means. And that's an important concept in ANOVA analysis. Analysis of variance. Analysis A, N, or AN analysis, O for of, VA variance, right? Analysis of variance. Analysis of variance, we essentially use these two things and we compare them to make more decisions, right, regarding business. So I'm going to go, at this point, I'm going to go ahead and delete that. Okay. So that's standard error there, and that's standard error there, right? You guys see it? Any questions on that? And if you have any questions, ask, right? Now, what's the next thing that we need? What is the question asking for here? The margin of error. So we need the margin of error, right? What is our level of confidence? What's our level of confidence? Why did I type 1 minus alpha here? Why did I type 1 minus alpha there? What is 1 minus alpha equal to, Trevor? A. We want to get our goal here is to get the margin of error, right?
Yeah.
Actually, I need to pull this down one more.
How do you pull it down?
You just grab it and pull it. Grab it on the side. Grab it on the side. What do we do on Tuesday when I wrote 1 minus alpha? Anybody remember? If you remember, raise your hand. 1 minus alpha. Ethan.
1 minus the confidence interval? Or the...
Well, 1 minus alpha was the confidence level. 1 minus alpha is the confidence level. If you guys don't know right now, in a couple weeks, you're going to wake up going, 1 minus alpha is the confidence level. When you wake up to come to school, you're going to go, 1 minus alpha is the confidence level. If there's 2 tails in the test or confidence interval, I divide the alpha by 2. You will be doing that when you wake up, seriously. It becomes second nature to you because I ask it over and over and over. Okay? Kid stats is a really difficult concept to teach and learn, right? So this is 0.95, right? So, Trevor, if 1 minus alpha equals 0.95, what does alpha equal?
0.05.
Yep. Right, so I'm going to do, if 1 minus alpha equal 0.95, subtract over 0.95, add over alpha, right? So alpha would equal 1 minus 0.95. Now, how many numbers in a confidence interval? There's 2, so what do we do with the alpha? We divide by 2. Because we need 2 critical values. Yep.
Show me the formula for the second
Right here?
No,
Over here?
yeah, that one.
Yeah. We're, instead of sorry, I'll start here. Here we're using sigma over square root of n, right? But if we don't know sigma, what do we got to use? An estimate of it, S. Right? Got it? Cool. So the standard error is this for the sigma known case, is that for the sigma unknown case, where you got to use the sample standard deviation. Now I'm going to write critical value here. Critical values. Okay. Oh, sorry. I forgot to divide alpha by 2. Okay, so we got to divide the alpha by 2, right? Okay, now why do I write critical values instead of z subscript alpha divided by 2? Why do I do that? I'm going to call this z alpha divided by 2. Right here. That's z alpha divided by 2. And this is t alpha divided by 2. Okay, these are subscripts, right? Maybe what I'll do is I'll subscript it. Okay. So what do? I need the critical values, right? I need these numbers. This is one number, and that's another number that's slightly bigger than this number here. This t is bigger than this. Why? What do we learn about the sample standard deviation? When we went from sample to sample, what happened? Some of you guys were above 5, right? How many people were above 5 on the sample standard deviation? Raise your hand. Raise your hand if you're above 5, right? Put your hand down if you're below 5. I'm below 5. Anybody else below 5 on the sample standard deviation? Okay. So sometimes we're below the sample standard deviation. Sometimes we're bigger. Sometimes sample standard deviation is below population standard deviation. Sometimes sample standard deviation is above the population standard deviation. Now, being above the population standard deviation means what? Which confidence interval is going to be wider? If we used a z here instead of a t, if s is bigger than sigma, this confidence interval's a little wider than this confidence interval, right? But what about the people where the standard deviation's less than sigma? Then this confidence interval, if we're using z, would be smaller than this confidence interval. So what do? We have to compensate for that possibility. So t values are slightly bigger than z values unless you have a sample size that is infinitely large. What is considered infinitely large in statistics for a sample size with regard to the t distribution? Does anybody remember? Anybody remember a t distribution? You guys remember your t distribution? Open up the t table. Do you guys remember this table?
Yeah.
Right? Down here, so 101 in degrees of freedom is considered infinity, right? What's it shaking? Weird. Oh, you guys clapping? Oh, somebody's probably jumping up and down up there, right? Shaking the room. Do we have an earthquake? You're not. So, a sample size of 102 is considered infinitely large for the t distribution, right? Because down here, that looks like the z value that corresponds to a lower tail probability of 0.05. 1.96 corresponds to the z-value when the lower tail probability is 0.025. Remember that from Tuesday? So down here, these are both z-values and t-values. All these values up here, well, no, these are all t's. All these are slightly bigger than what? Than the z-value, right? All these values here are slightly bigger than their corresponding values down here, right? So these are t-values. And these are t-values. Why are these t-values so freaking big? Why are they so big? Because you got a sample of 2 there, right? N minus 1 is, N minus 1, if N is 2, N minus 1 is 1. 2 minus 1 is 1, right? So you have a sample size of 2. How big do you think your sample standard deviation is going to be? How much error do you think is going to be in it? In your standard deviation of the sample if you only have 2 observations? Oh, it's going to be huge, right? Because who could be in your sample of 2? Maybe Kobe Bryant went to dinner in Atlanta, and you asked him how much money he spent. And then you ask Chandler how much you spent. There's a big variance there, right? He might have spent $5,000 for his dinner, where you might spend $25,000. There's a big, huge, right? Or maybe you ask Chandler and Cassie, maybe you guys both spent $25 in that sample of 2. What's your variance then if both spend 25? Your mean's 25. 25 minus 25 squared is 0. Plus 25 minus 25 squared is 0. Divide that by 1, right? 0. So if in a sample of 2, maybe you end up with Cassie and Chandler in your sample, and you got a variance of 0 because they both spent $25. But maybe in your a sample of 2, you got Kobe Bryant in there with Chandler. $1,000 versus $1,010 versus $10, right? So what's the average?
55.
Oh, how about 990? How about 990 for Kobe and $10 for Chandler? It'd be 500, wouldn't it?
Yeah, around that.
Yeah, it'd be 500. Because 0 and 1,000 would be 500, right? So that average would be 500. 10 minus 500 is huge. Square it, even bigger. 990 minus 500, huge. Square it, even bigger. So you got this huge variance versus a 0 variance. So is that providing a very good estimate of the population standard deviation? No. Right? So that's why as the sample size gets smaller and smaller and smaller, you need more and more play it safe. Play it safe. You need more play it safe. Right? You need to play it safer. You need to allow for the error in the standard deviation to freaking grow, right? Also, you got error in the sample mean, right? A sample of 500 is much different than a sample mean of 26, right? 26.56. So let's get the, whoops. I'm hitting the wrong thing. Okay, does anybody remember the critical value for z when alpha divided by 2 is 0.025? What is it? 1.96. Let's review how we got that. We'll open up the z table. You might want to open up this table, it's a little better. So in this table, what do you do?
Go to 1.9.
Well, you want to find 0.025, right? What row is 0.025 in?
106.
Row 1.9. And what column?
106.
06. So 1.96, right? So, you are correct, sir, as Ed McMahon would say to Johnny Carson all the time. You guys are way too young for that show. Okay, now what about the t-table? If for some reason sigma's unknown, right? If I put in a question mark here, what's going to happen? If sigma's unknown, what's going to happen? Aye. What happened?
Got rid of our standard.
You can't calculate that, can you? Yeah! Excel just had a heart attack. Right? What does Tommy Boy do? He tries to beat his chest to get his heart going again?
Yeah.
Is that right? Okay. So if sigma's unknown, you can't use that confidence interval, can you? So let's go to the, if you don't know sigma, you can't use Z, you got to use T, yo. And where's the T values located? Are T values located in the Z table? Why do I call this a Z table? Because the number line here, Z, right?
So you have to go to the T table
So you have to go to the T table.
and open that up.
Yeah, we go to the T table. Here's a T table, right? Nice clean T table. What is my alpha divided by 2? What's my alpha divided by 2? So how many probability values are in a T table? 3, 4, 5, 6. Very common p-values, right?
Yep.
How many p-values are in a Z table?
10.
Well, we got 1, 2, 10 in each row, right? How many rows do we got? Well, on this page we got 31, right? On that page we got 31. So what is 32 times 10? 31 times 2, 62 times 10. We have over 600 p-values in a Z table, right? But how many p-values do we have in a T table? In this one, 6. Okay? So this is the alpha divided by 2 for our case. Sometimes you want to use the alpha column. But we have a confidence interval, so we use the alpha divided by 2 column, right? 0.025. Now, how far do we go down? What is the degrees of freedom over here? What are the degrees of freedom equal to? N minus 1. Why is that? What is the difference between this confidence interval and that confidence interval? What is one of the primary differences? What's the difference?
S and
Yeah, we're using sample size or sample standard deviation to estimate population standard deviation, right? So, go to my website again. I want you to open up PowerPoint 3. This is a little review. Do you guys remember the equation for the sample standard deviation? Oh! The difference between VAR dot P is that we divide by N, right? VAR dot S, what's the difference between VAR dot P in Excel and VAR dot S in Excel?
divide N by 1. N minus 1.
You divide the sum of deviation squared by N minus 1. Those are your degrees of freedom. So how big's our sample size?
5.
Our sample size is 49, so our degrees of freedom are, does everybody understand that? Everybody say it. Degrees of freedom equals
48.
48!
48.
48! Why 48?
Because it's 1 lower than the 49.
And the 49 is the sample size N.
Yep.
Now, let me ask you a question here. As N gets bigger and bigger and bigger, 101, 1,000, 1,000,000, does little n get closer and closer and closer to big N, the population size? Because if we're talking about 300 million Americans and N is 10, 10 is really small compared to 300 million, right? But as little n gets bigger and bigger and bigger, million, 100 million, 300 million, what has happened? Well, we're no longer calculating the sample variance. If little n becomes big N, we're calculating the population variance, which is why as our sample size gets bigger and bigger and bigger, as the sample size gets bigger and bigger and bigger, what happens to degrees of freedom? Bigger and bigger and bigger. So the t-distribution is getting closer and closer and closer to what? The t-distribution is getting really close to the standard normal distribution. Why does the t-distribution get so close to the standard normal distribution, the z-distribution? Why? Because the standard deviation is getting really, really close to the population standard deviation. So as it gets bigger, the standard deviation of the sample gets closer and closer and closer to the population standard deviation, right? So here's the last thing, right? So the z value is what? You guys notice that? What column must I be in here? 0.025? What row do I have to be in to get the t value though? So in column 0.025, 48 is 2.011 kind of close to 1.96? Yeah. So my margin of error is what? For the sigma known problem, my margin of error is equal to what?
That minus.
That times the z value times standard error, right? What's my estimated margin of error? My estimated margin of error is 1.4067. Wow, that's pretty close to 1.4, right?
Yeah.
Why? Because my sample standard deviation is pretty close to truth. Does everybody have the same margin of error?
Will you do that one more time?
Yeah. What am I doing? I'm taking z times the standard error, right?
Okay.
T times the standard error. So this right here is z times the standard error, right?
Okay.
And this is t times the standard error. What do you guys have for, what does everybody have for the margin of error when sigma's known? Everybody? Everybody has the same value, right? Why? Because from sample to sample, 5 doesn't change, right? What about the margin of error? Is some people below, how many people are above 1.4? How many people are below 1.4? If you're below 1.4, how far below are you? Not much, right? Now what about the confidence interval? What about the confidence interval? What do you do? The sample mean minus the margin of error. You guys see it? That's the lower limit. The sample mean, x bar, plus the margin of error, the estimated margin of error. Whoops, I did something wrong. Sorry. This is the lower limit for the sigma known case. The upper limit for the sigma known case is the sample mean plus the margin of error, right? Then over here, the lower limit for the sigma unknown case is the sample mean minus the estimated margin of error, right? Okay, so these two numbers are pretty close to these two numbers, right?
Yep.
So let me ask one last question. What's the probability that mu is in this interval right here? What's the probability that mu is in that interval? Nope. Let me demonstrate something real quick. Zeus says what? Hal and his students. Mu is equal to 30. Okay, what's the probability that 30 is in this interval? 0. It's not in there. Right? What happens if Zeus says this now? Sorry, Hal and his classmates, or students. I played a trick on you. Mu is really 20. What's probably that 20 is in this interval?
0.
0. Ha ha ha. I'm Zeus. I like to play jokes. Mu is really 26.
1.
What's probably that mu is in that interval? 100%. It's in there. Now, how many people, suppose the true mean is 25.2. Suppose the true mean is 25.2. Is it in my interval? How many people with 25.2, how many people have 25.2 in their interval? How many people? Raise your hand if you got 25.2 in your interval. Okay, right? So what's going on here? If we replicate this experiment 1,000 times, how many intervals? We got about, what, 20 intervals in here? If we did this 1,000 times, right? How many of those intervals would have the true mean in it? 95%. So if we did this 1,000 times, we expect 950 of those confidence intervals to contain the true value. 25 of those confidence intervals, the true value would be above the confidence interval. For 25 of those 1,000 intervals, the true mean would be below that confidence interval, those confidence intervals, or that whatever, right? So 950 out of 1,000, if we do this 950,000 times, or 1,000 times, 950 of those will contain truth. How many times are you gonna do this in real life? Once, maybe twice, most likely once. Do you have a pretty good chance of having an interval that contains truth? Yeah, if you use a 95% confidence interval. Suppose you used a 1,000% confidence interval. 100% confidence interval. If you use a 100% confidence interval, is mu going to be in your interval?
Yes.
Yes. Why?
You're 100%.
Yeah. What happens to these values if you're using a 100% confidence interval? What is that?
Identical.
Infinity. What's the probability of being greater than 1.96 if you're using a 100% confidence interval? 0. What's the probability that you're less than negative 1.96? 0. What's the probability that you're between negative 1.96, what's the probability that you're between the z values that correspond to a 100% confidence interval? 100%. But your confidence interval will be infinitely wide. And what is infinity times the margin of error? Infinity. So if you use 100% confidence interval, what would you have here? If you use 100% confidence interval, you'd have negative infinity, and you'd have positive infinity, right? If you used a 100% confidence interval, these two numbers would be negative infinity and positive infinity, right? How can you use that to make a decision? You can't, right? So do you want to be 100% sure in statistics? No, you don't want to be 100% confident. You want to be what? 99% confident, 95% confident, maybe 90% confident. If your product's gonna kill somebody, you want to be really confident, maybe 99% confident. But if your product is how many chips are in a Chip Soy cookie, are you gonna kill anybody with chips? So maybe use a 90% confidence interval. All right. New